Numerical number 8. The band gap of silicon is 1.15 electron volt. Find the temperature at which the number of electrons in the conduction band of silicon are doubled over the number of electrons in it at T equals to 300 Kelvin. Let's write what is given here. Band gap of silicon is given, which is 1.15 electron volt. Temperature is 300 Kelvin, and we have to find the temperature T1 when electrons double. That's what we have to find. We have the equation for finding the electrons equals to Nc into E raised to minus of Ec minus Ef upon KT. This we can modify to N equals to Nc e raised to minus of Eg upon twice KT. As you know that this Ec minus Ef is half the band gap, Eg by 2. Ec is lowest energy level in the conduction band, and Ef is the Fermi energy level, which is in middle of the energy gap for the intrinsic semiconductor. And so this difference is equals to Eg by 2. Let us substitute the values when the temperature is 300 Kelvin. So this equation we can write as N equals to Nc e raised to minus Eg, that is minus 1.15 divided by twice Kt. So this is 2 into Kt is 0.0258 Kt. K is Boltzmann constant, which is 8.6 into 10 raised to minus 5 electron volt per Kelvin into temperature. In this case it is 300 Kelvin. So that comes around 0.0258 electron volt, the value of KT. Let us simplify this further. Therefore, N equals to Nc into E raised to this E raised to we get minus 22.287. If you simplify this, you get minus of 22.287. This is at temperature 300 Kelvin. Then the second part is temperature is T1 now. And in this case, electrons are double. Electrons are double. Concentration of electrons is double at temperature T1. That is, at this temperature, N becomes equals to 2N. Therefore, this 2N is equals to Nc into E raised to minus of Eg upon twice Kt. Let us substitute the values of band gap. So this is 2N is equals to Nc e raised to minus of 1.15 divided by, here is the temperature T1 now. So 2 into K, that is 8.6 into 10 raised to minus 5 into T1. And let us simplify it. You get Nc into E raised to minus of 6686 upon T1 after simplification. So this is equals to 2N. Let us say this is our equation 2 and this is our equation 1. Then divide equation 2 by equation 1. Equation 2 divided by equation 1. So left hand side of the equation 2 is 2n. Left hand side of equation 1 is n. So 2n divided by n, which is equals to nc e raised to minus of 6686 upon t1 divided by nc into e raised to minus of 22.287. That is the equation 1. So this is nothing but 2 equals to e raised to minus of 6686 upon t1 upon e raised to minus of 22.287. Let's take natural log on both sides. So that would be ln of 2 equals to minus of 6686 upon t1 plus 22.287. We can simplify it further. 6686 upon t1 equals to 22.287 minus ln of 2. Ln of 2 is 0.693 and that is equals to 21.594. So T1 is 6686 upon 21.594, that comes around 309.6 Kelvin. So temperature is 309.6 Kelvin when electron concentration doubles. Let's go to the next problem. The conductivity of pure silicon increases by 60% when the temperature is increased from 25 degrees Celsius to 30 degrees Celsius. Calculate the energy gap in silicon from this data. So this is related to the conductivity, and we know the relation for conductivity is sigma is equals to sigma naught e raised to minus of Eg upon 2 kT. So this is the equation for conductivity. Now there is a conductivity at 25 degree and conductivity at 30 degree. So let us find the conductivity at 25 degrees Celsius. So at 25 degrees Celsius, that is 25 plus 273, which is equals to 298 Kelvin. So we will find the conductivity at 298 Kelvin. So this sigma is equals to sigma naught e raised to minus of Eg upon twice kT upon twice kT. Let us write the values of this k and t. So 2 into 8.6 into 10 raised to minus 5 into temperature is 298. Let's simplify it further. So sigma naught e raised to minus of Eg, and value of this multiplication is 0.05126. Let's say this is our equation 1. So this is conductivity at temperature 25 degrees Celsius. Then at temperature 30 degrees Celsius, that is 30 plus 273, which is equals to 303 Kelvin. And at this temperature, conductivity increases by 60%. Conductivity increases by 60%. That is, sigma becomes equals to 1.6 sigma. So let us write the conductivity relation at 30 degrees Celsius. So sigma is now 1.6 sigma equals to sigma naught into e raised to minus of Ag upon twice kT, or 1.6 sigma. Let us write properly. So 1.6 sigma equals to sigma naught e raised to minus of Ag upon 2 into 8.6 into 10 raised to minus 5 into temperature, in this case is 303 Kelvin. That is equals to sigma naught e raised to minus of Eg upon, so this multiplication is equals to 0.05211, and this is equals to 1.6 sigma. Let us say this is equation 2. So we got equation 1 here and equation 2. What we are going to do is equation 2 divided by equation 1. Equation 2 by equation 1. So 1.6 sigma divided by sigma is equals to sigma naught e raised to minus of Eg upon 0.05211 divided by this quantity sigma naught e raised to minus of Eg upon 0.05126, that is 1.6 equals to e raised to minus of Eg upon 0.05211 divided by e raised to minus of Eg upon 0.0516. To simplify this, we have to take natural log on both sides. Take natural log on both sides. So this is ln of 1.6, which is equals to minus Eg upon 0.05211 plus Eg upon 0.05126. ln of 1.6 is 4.47, and that is equals to, let's take Eg common, simplify this, rearrange it. So 1 upon 0.05126 minus 1 upon 0.05211, and this is equals to Eg into 0.3182, and therefore band gap Eg is equals to 0.47 divided by 0.3182, that is equals to 1.47 electron volt. So band gap of the silicon is 1.47 electron volt at temperature 30 degrees Celsius. The next sum, a semiconductor crystal 12 long, 5 wide, and 1 thick has a magnetic flux density of 0.5 Weber per meter square applied from front to back perpendicular to the largest faces. When a current of 20 milliampere flows lengthwise through the specimen, the voltage measured across its width is found to be 37 microvolt. What is the Hall coefficient of this semiconductor? Let's first write what are the given quantities here. Length of the semiconducting crystal is given, which is 12 Width is given, which is 5 and the thickness is given. Let's denote it by D, is equals to 1 Then magnetic field is given B, zero point 0.5 Weber per meter square. Then current I, which is flowing through the semiconductor, is given 20 milliampere, that is 20 into 10 to power minus 3 ampere. And also Hall potential is given, which is 37 microvolt, or we can say 37 into 10 raised to minus 6 volt. We have the relation for Hall coefficient RH is equals to VH into D divided by V into I. VH is 37 into 10 raised to minus 6 volt into D is 1 that is 1 into 10 to power minus 3 meter divided by BI. B is 0.5 Weber per meter square into I. I is 20 into 10 raised to minus 3 ampere. If you simplify this, you get 37 into 10 raised to minus 9 divided by 10 to power minus 2, and that is equals to 3.7 into 10 raised to minus 6 meter cube per coulomb, and this is the Hall coefficient. Next sum is also based on the Hall effect. Hall coefficient of certain silicon specimen was found to be minus 7.35 into 10 to power minus 5. Here is 10 to power minus 5. So this Hall coefficient is given. RH is equals to minus 7.35 into 10 to power minus 5 meter cube per coulomb from 100 to 400 Kelvin. Determine the nature of semiconductor. Okay, nature of semiconductor. Nature of semiconductor means whether it is N-type semiconductor or P-type semiconductor. The value of Hall coefficient is negative, and so this is N-type semiconductor. So nature of semiconductor is N-type. Why? Because RH is negative for N-type semiconductor. If conductivity was found to be, okay, now the conductivity is also given, sigma is equals to 200 per ohm meter, or you can say 200 Siemens per meter. Calculate the density and mobility of the charge carrier. We have to calculate density and mobility, UE. In this case, this is N-type semiconductor, so charge carriers are electrons, so we have to find mu e, the mobility of electrons. We know the relation for RH is equals to 1 upon n into E. And from this we can get n equals to 1 upon RH into E, which is RH is 7.35 into 10 raised to minus 5. Into charge is 1.6 into 10 raised to minus 19. Here I have not considered negative sign of RH. Negative sign of RH just indicate that whether it is a p-type semiconductor or n-type semiconductor. You don't have to consider that polarity in calculations. So this is equals to 1 upon 11.76 into 10 raised to minus 24. If you simplify it further, you get 8.5 into 10 raised to 22 per meter cube. So number of electrons in this case in the n-type semiconductor is 8.5 into 10 to power 22 per meter cube. Now for the conductivity. Conductivity in terms of mobility is sigma equals to Ne, or you can say Nie, into mu E plus mu H. But this is n-type semiconductor, so this is equals to Ne into mu E for n-type semiconductor, and that is sigma. And what we have to calculate is mu E is equals to sigma upon Nie. So sigma is given, which is 200 per ohm meter divided by Ni. We have calculated the number of electrons here, which is 8.5 into 10 to power 22 into the charge of the electron 1.6 into 10 raised to minus 19. If you simplify it, that is 200 upon 13.6 into 10 raised to 3, which is equals to 1.47 into 10 to power minus 2 meter square force per seconds. So this is the mobility of electrons in this n-type semiconductor.